When we seriously discuss the existence of extraterrestrial life, we inevitably begin to wonder, are we studying exoplanets to find another civilization, or to discover our own place in the universe? It is a long story, so let us start with a dream. Before we dive in, please remember to like and share this content. The star we are talking about today is Barnard's star, located only about 6 light-years away from Earth. It is one of our closest neighbors in the Milky Way, second only to the Alpha Centauri system. Unlike that complex multi-star system, Barnard's star is an isolated celestial body. It is classified as a red dwarf, which is the most common type of star in our galaxy. Despite their abundance, red dwarfs are difficult to observe directly because of their relatively low luminosity. For instance, the mass of Barnard's star is only about 16% of our Sun's mass, and its brightness is less than 0.04% of the Sun's. Consequently, it is invisible to the naked eye. The physical characteristics of Barnard's star distinguish it from larger and hotter stars. Its surface temperature is approximately 5,400 degrees Fahrenheit, compared to the Sun's surface temperature of about 9,900 degrees. Barnard's star primarily emits infrared radiation, and its energy output is quite low. This means any potential planet orbiting it would need to be much closer to the star than Earth is to the Sun to receive the same amount of energy. One of its most exciting features is its unusual path across the sky. Its proper motion exceeds 10 arcseconds per year, making it the fastest moving star relative to our solar system. This rapid movement is due to its proximity and high velocity as it travels through the galaxy at about 50 miles per second relative to the Sun. For astronomers, this motion has been a primary reason for close observation for over a century. Its trajectory is so precisely mapped that scientists can predict its future movement with accuracy. The star will continue to approach our solar system, and in about 10,000 years, it will reach its closest point at approximately 3.75 light-years. The story of this star began in 1916 when astronomer Edward Emerson Barnard first noticed its unique motion. He measured the displacement of this object against the background of distant stars and realized it was moving faster than any other object observed at the time. This discovery was groundbreaking, proving that relatively nearby stars could travel at significant speeds. For decades, it remained a primary target for study. In the 1960s, because it is so close to Earth, the first attempts were made to find planets around it. Early searches focused on detecting gas giants similar to Jupiter or Saturn. However, the methods available then, particularly astrometry, were not yet refined. Astrometry seeks to find planets by measuring the tiny wobbles in a star's position caused by the gravitational pull of an orbiting body. The challenge was that the technology was in its early stages, leading to significant measurement errors. Despite these limitations, astronomers like Peter van de Kamp claimed to have detected planets using this method during the 60s and 70s. His team believed they found a gas giant several times more massive than Jupiter. This news sparked excitement because it suggested that red dwarfs could host large planets. However, subsequent studies questioned these findings. As technology improved, it became clear that the initial data was inaccurate. The observed wobbles were likely caused by instrument errors or other noise rather than planets. By the 1980s, the idea of a massive planet orbiting Barnard's star was largely debunked. Astronomers had to rethink their approach. Over the following decades, more sophisticated tools were developed, such as the radial velocity method. This technique indirectly detects planets by observing changes in a star's spectrum as it moves slightly toward or away from Earth. This method proved much more reliable. By the 1990s, These new techniques replaced astrometry as the primary tool for finding planetary systems. Yet, for a long time, no planets were found around Barnard's star, which puzzled the scientific community, especially since other red dwarfs like Proxima Centauri were found to have planets, including some in the habitable zone. In the late 2010s, technological advances, specifically the development of more sensitive spectrometers, allowed astronomers to revisit the star. In 2018, researchers announced the discovery of a super-Earth orbiting Barnard's star. This rediscovery was based on radial velocity data and suggested that while there were no gas giants, small rocky planets did exist. The data tracked the star's wobble by observing redshift and blueshift in its light. Initially, it was thought this planet orbited at about 0.4 astronomical units from the star. However, by 2021, deeper analysis showed the signal was not from a planet but from the star itself. Internal activity and changes within the star created color variations that mimicked the signal of a planet. Essentially, the suspected planet was a result of stellar activity. By 2022, further research confirmed that the super-Earth did not exist, marking another failure in the search. A turning point finally arrived in October 2024. After decades of exploration, astronomers officially confirmed a planet orbiting Barnard's star, named Barnard B. Unlike previous speculative studies, this discovery was based on high-precision modern instruments. The breakthrough came from using the most accurate spectrometers available, such as those at the European Southern Observatory. These tools allowed scientists to detect extremely faint wobbles that were previously undetectable. Barnard B is relatively small, with a mass about 37% of Earth's, but its subtle gravitational influence confirmed its existence. This discovery is supported by vast amounts of data and has been verified by independent teams worldwide. The orbital period of Barnard B is incredibly short, lasting only about 3 days. This means it is much closer to its star than Mercury is to our Sun, at a distance of only 0.04 astronomical units. Such proximity creates an extremely harsh environment. Tidal forces from the star's gravity cause internal friction, heating the planet's core. Combined with intense radiation, the surface conditions are brutal. As a red dwarf, the star emits significant radiation, heating the planet's surface to approximately 260 degrees Fahrenheit. This high temperature makes the planet uninhabitable for life as we know it, as liquid water cannot exist. Despite the high temperatures, the discovery of Barnard B opens new pathways for studying planets around red dwarfs. Its small size and extreme orbit suggest that rocky planets might be more common around such stars than previously thought. While Barnard B is not habitable, the question of habitability remains fascinating in the context of red dwarfs. Future research may focus on finding planets further out in the system's habitable zone, where temperatures might allow for liquid water. However, the presence of life is further challenged by the star's tendency to release flares. While Barnard's star is less active than some other red dwarfs, it still emits ultraviolet radiation that can strip away a planet's atmosphere over time. This phenomenon has been observed in other systems, reducing the likelihood of life even on planets that seem promising. For Barnard B, any atmosphere or surface water it might have once had was likely lost long ago due to this stellar activity. Red dwarfs, also known as M-type stars, make up about 70% of the stars in the Milky Way. Their stability and long lifespans make them primary targets for exoplanet research, as they provide a long window for planetary evolution. Some systems, like TRAPPIST-1, have been found with multiple Earth-like planets, raising hopes for finding liquid water elsewhere. However, red dwarfs also present major challenges, primarily their unpredictable flares and the issue of tidal locking. Because planets must be close to a red dwarf to stay warm, they often become tidally locked, with one side always facing the star and the other in permanent darkness. This creates extreme temperature differences between the two hemispheres. Despite these hurdles, the sheer number of red dwarfs in our galaxy means that if even a small fraction of their planets retain atmospheres, the number of habitable worlds could be vast. The discovery of Barnard B is a significant step forward, proving that even in systems where previous searches failed, the right tools can reveal new worlds. As the second closest star system to our Sun, Barnard's star is perfect for detailed observation. Future studies will likely focus on the precise composition of Barnard B. With advanced tools like the James Webb Space Telescope and next-generation ground observatories, astronomers will be able to study atmospheres and collect more data on surface conditions. This discovery is part of a larger effort to map the planetary neighbors of our universe. Astronomers hope to find not just one, but potentially multiple planets around Barnard's star, providing key clues to the formation and evolution of planets in the most common yet least understood systems in our galaxy. We are moving from the relatively tranquil neighborhood of Barnard's star to the king of our solar system. When we gaze at this giant, we aren't just looking at a planet, we are looking at a complex, high-energy system that challenges every concept of weather we have on Earth. This is Jupiter, the solar system's largest planet, a gas giant that acts as a world unto itself. Jupiter's atmosphere is organized into a stunning array of east-west jet streams that alternate as they wrap around the globe, growing in intensity from the equator toward the poles. In the brighter regions, known as zones, ammonia ice clouds rise from below, reflecting sunlight in shades of white and pale gold. In the darker belts, the air is cooler and descending, allowing us to see deeper into the atmosphere. Here, compounds like ammonium hydrosulfide stain the clouds in rust and ochre tones. Each neighboring band moves in the opposite direction to the one next to it, a vast planetary pattern carved by ferocious winds. These jet streams can reach speeds of hundreds of miles per hour, far exceeding any hurricane on Earth, with some atmospheric temperatures clocked at over 400 miles per hour. On this rapidly rotating sphere, the Coriolis effect splits the atmosphere into dozens of these jet streams, creating a system of cyclones and anticyclones fueled by heat rising from the planet's interior. Between these colorful cloud bands lies the most famous storm in the universe, the Great Red Spot. This salmon-colored oval-shaped anticyclone has been raging in Jupiter's southern hemisphere for centuries. It is large enough to swallow the Earth whole. As a high-pressure vortex, it rotates counterclockwise, towering high above the surrounding clouds. Its deep reddish hue remains a bit of a chemical mystery, likely caused by complex organic molecules or sulfur compounds dredged up from deep within the atmosphere. At its edges, winds scream at up to 268 miles per hour. While observers have noticed the Great Red Spot shrinking and changing shape in recent decades, it was once twice its current size. It remains the dominant feature of the Jovian sky. Beyond the Great Red Spot, the entire atmosphere is a turbulent tapestry of smaller storms and eddies. We see long white ovals, which are smaller anticyclones that can last for decades. In 2000, 3 of these merged to form Oval BA, also known as the Little Red Spot. At the boundaries of the jet streams, wind shear creates twisted, filament-like patterns and wavy clouds known as Kelvin-Helmholtz waves. Because there is no solid surface to provide friction, these storms can last much longer than anything we see on Earth. Near the poles, the chaos gives way to a surprising geometric order. The Juno spacecraft discovered that Jupiter's poles are crowned by clusters of giant cyclones arranged in perfect symmetry, an octagon of storms at the North Pole and a hexagon at the south, each thousands of miles wide, sitting side by side without ever merging. The drama continues with Jovian lightning. For a long time, we knew lightning occurred deep in the water cloud layers, similar to Earth's storms. However, Juno discovered shallow lightning high in the atmosphere. In these freezing upper reaches, ammonia acts as an antifreeze, allowing for liquid ammonia water droplets even at -126 degrees Fahrenheit. When ice crystals collide with these ammonia water droplets, they generate static electricity, causing lightning to crackle much higher than previously thought possible. These flashes, though lasting only milliseconds, are as bright as terrestrial lightning and help solve the mystery of why ammonia seems to vanish from certain parts of the upper atmosphere. It is being carried deep into the interior by mushballs of icy hail. Looking even higher above the clouds, Jupiter wears a crown of the most powerful auroras in the solar system. These blue-violet glows are hundreds of times more energetic than Earth's northern lights and, unlike ours, they never stop. They are driven by Jupiter's massive magnetic field, thousands of times stronger than Earth's, and its rapid 10-hour rotation. This magnetic field traps charged particles, many of which come from the volcanic moon Io, and funnels them toward the poles. Interestingly, these auroras leave footprints, bright spots in the light that correspond to the magnetic connections between Jupiter and its moons like Io, Europa, and Ganymede. Finally, if we step back even further, we see something unexpected, a faint, gossamer ring system. Discovered only in 1979, these rings are made of fine dust rather than the bright ice chunks found around Saturn. They are almost invisible, a million times fainter than the planet itself. These rings are maintained by Jupiter's small inner moons, like Hydra and Metis. When micrometeoroids strike these tiny moons, they kick up dust that drifts into orbit, replenishing the rings. This is Jupiter, a magnificent, brutal world where the atmosphere, magnetic field, rings, and moons are all bound together in a complex dance of gravity and electromagnetic force. That concludes our journey for today. I hope this brings you sweet dreams of the cosmos, and I will see you next time.